We will do a small lecture on the combination of waves. Now, these are taken from the notes of Gabriel Brownstein from University of Central Florida. So this gives rise what we talk about a little bit on interference and a little bit on coherence. So in general, what happens is that, this is high school physics. It is being reiterated here for completeness. When we combine two waves to form a composite wave, okay? So the composite wave is basically the algebraic sum of the two original waves point by point in space. So this is like called the superposition principle. So when we add the two waves, we need to take into account obviously their direction, their amplitude, and their phase. So for example, here is a red is one wave, then the blue is another wave. These waves are in phase, as we can see, with each other. They almost have the same amplitude and the same direction. As a result of that, the resultant wave is amplified. It's basically the algebraic sum of the two original waves, okay, where the amplitude is doubled. Essentially, the phase remains the same and the direction also remains the same. So this is what you get when you do this principle of superposition. So it is called the principle of superposition, which is nothing but the algebraic sum of the two waves. All right. Now, when the two combining of the two waves to form a composite wave in optical parlance, it is called interference. So here you can see that there are two waves which are almost in phase, the red and the blue, what we showed, almost in phase. Okay, there's a little bit of a phase jitter, as you can see. So the result is basically what we call a constructive interference, in which the waves basically reinforce each other. You had two smaller waves and they kind of give rise to a very large wave. Okay, so this is constructive interference, and the phenomena of combining the two waves is called interference in general. All right. So based on this, if we move along, now if the two waves have like pi out of phase, okay, so they are pi out of phase, okay. So as you can see, the trough of this wave is actually like kind of half of this when it is actually rising. So this is shifted. There is a phase shift, right? Ideally, if this was here, the trough of the blue wave was at this particular dotted line, then they would have been in phase. Otherwise, now they are pi out of phase. As a result of that, the waves almost cancel each other. So what we call destructive interference. When the interference is destructive, the waves cancel each other. It's as simple as that. It's cancellation. Okay, like you had an addition effect here, it is a cancellation, right? So when they are in phase, they do give rise to constructive interference, as you can see. When they are pi out of phase, the waves cancel each other and you get what we call destructive interference. So this is very simple logic and very simple math. Now, this is what we are going to use in PDPA, LDV, and all these other cases where so how is this achieved? Okay, so when light waves travel in different paths and then they are recombined, they interfere. So for example, this is a common light source, say for example, and one beam of one ray of light passes directly like this. The other is reflected and ultimately brought in the same direction to the detector, but it passes through a couple of mirrors, and as a result of that, it traverses a little bit extra in terms of the path that it takes. Here the path is from A to B. Here it takes A, C, D, and then B. Okay. So if each wave has an electric field whose amplitude goes as E is equal to E naught into the sine term, okay, and then this is the vector, this is the unit vector. The S measures the distance traveled along each wave's path. So what happens is that when in this case when the waves when these two waves actually recombine with each other, okay, so if the light paths differ by an integer multiple of the wavelength, that is this delta S, this additional path that the wave travels, that is, one wave travels more than the other. So if S is the path, the number 2 ray travels a little bit extra than number 1. So there is a delta S difference in the light path. So this delta S difference, if it is an integral multiple of the wavelength, which is lambda, okay, then you get constructive interference. So no matter what, the waves may vary by quite a bit of a path length, okay, or several, but these are still small because you see lambda is small. Lambda is a small number usually for light. So if they vary by some integer multiples, so even when these waves actually combine with each other, you tend to get this, what we call this constructive interference. So the path length or the difference in path length has to be an integral multiple of lambda. Okay, that is what you need to take into consideration. If if that is the case, then you get this constructive interference. If that is not the case, okay, then you get what we call, so destructive interference occurs when the light paths differ by an odd multiple now of half the wavelength. So if this delta S, which is again the path difference between beam 1 or ray 1 and ray 2, if it is like an odd multiple, that is why you have 2m plus 1 of lambda by 2, you get a destructive interference. So this is the logic. Once you get the destructive interference, you get this, there is nothing, right? So let's talk a little bit about now temporal coherence time and spatial coherence length. So temporal, this is taken from the notes of Rick. All right. So you can see that this is taken from Professor Rick Trevino's lecture at Georgia Tech. So the temporal coherence time is how long the beam remains sinusoidal at a single wavelength. So this is what is temporal coherence is all about. So the temporal coherence time is, say, tau c. So this is the time, this small period is the time that the beam remains sinusoidal at a single wavelength. So this is the wavefront and this is the direction of propagation. So the temporal coherence time is that short time in the time that the beam remains completely sinusoidal at a single wavelength. Spatial coherence length is basically the transverse distance, or this distance, over which the beam wavefronts remain flat. Okay, so this is spatial coherence length xc. So this is the transverse distance, understand this, transverse distance over which this beam fronts, this is a beam front, for example, this wiggly lines that you see, over which the beam fronts remain flat. But there are two transverse dimensions, okay, because x and y, and therefore we can define a spatial coherence area, which is called AC as well. So temporal coherence is the time that the beam remains sinusoidal, okay, at a single wavelength, and spatial coherence is the distance in the transverse direction over which the wavefront remains flat. Okay, so this is the two definitions of this. So if you look at spatial and temporal coherence, what you see that this particular front, for example, is spatial and temporal coherent, because this is the TC, this is the XC. Okay, this is the time at which the wavefront remains sinusoidal at a particular wavelength, XC. Now, if you look at this particular picture, you will see this is temporally coherent but spatially incoherent, because the spatial incoherence is just a small length and this is the temporal coherence. Okay, so it maintains that. Okay, and then you have spatial coherence but temporal incoherence. So as you can see, this particular frequency changes, so it cannot maintain, it only maintains a single sinusoidal wave up to a particular very small duration of time before it changes, but the XC is temporally coherent, the wavefront. And this is both spatial and temporal incoherence, where you have both actually varies, okay, after a short time and distance. So the beams can be coherent or partially coherent, indeed even incoherent in both space and time. These are some of the examples. These are the wavefronts, and this is how we have explained this. Okay. So how quickly will a light deviate from its perfect sine wave in time? Okay, so let us assume that the light wave has two frequencies. One is omega 1, one is omega 2. Okay, so let's assume that these are the two frequencies that you have. All right. Okay, so this is the E total, which is the real part of this. So the two frequencies will become significantly out of phase. Remember, they will become so these are the two waves basically. Okay, so they have a little bit of a phase difference to start with, right? Omega 1 and omega 2, and they have a so the waves have different frequencies. Sorry, they have different frequencies to start with. All right, not necessarily have an initial phase, but they have different frequencies. They start all from the same point, but they have different frequencies. Now, these two frequencies will become significantly out of phase with each other over a time period, say tau c. Okay, this is Tc or tau c. So this is basically omega 1 multiplied by tau c minus omega 2 multiplied by tau c is equal to 2 pi, because that is the significantly out of phase definition. So in other words, tau c becomes 2 pi divided by omega 1 minus omega 2. So the phase will drift, okay? The phase will drift on a time scale which is 2 pi by delta omega, which is nothing but 1 over the frequency, the delta frequency, because delta omega is nothing but 2 pi into the delta frequency. All right. So the two waves will become significantly out of phase over a time scale which is given as tau c, which is nothing but 2 pi, but the frequency difference between the two waves. All right. So this is how quickly a sine wave will deviate from a perfect sine wave in time. Okay. So assume that it starts as a perfect sine wave. In a very short time, because it has got two frequencies, it will drift. Okay, the phase will drift. Okay? So this is exactly what happens in this particular case. So the coherence time is therefore the reciprocal of the bandwidth, or other words, the largest frequency difference in the light wave will yield the shortest drift time, because it is inverse over the frequency difference. So larger are the frequencies in the light wave, more will be the drift in time. Okay, or shortest will be the drift time. So this coherence time becomes very small if the frequency drift, or the largest frequency difference between in the light wave, is very large. So delta frequency is a light bandwidth, the width of the spectrum. So you can see the sunlight and light bulbs, which has got all kinds of frequencies, are temporally very incoherent. Okay, very, very small coherence times, because the bandwidths are very large, because it is the entire visible spectrum. So the entire visible spectrum, if you take, is like several hundreds nanometers. Okay, so if you divide and if you convert that to the corresponding frequency scale, you get a coherence time which is very, very short. On the other hand, the lasers have got very low frequency difference, because it's monochromatic to begin with. It's that delta frequency change is very, 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 very small. As a result of that, the coherence time is rather large. It is as big as a second, which is amazing, because this is more than 10 to the power of 14 cycles, for example. Up to 14 cycles, 10 to the power of 14 cycles, you can actually maintain the coherence of a laser beam. Understand? So two things that you should understand over here: the coherence time is reciprocal of the bandwidth for lasers, because the bandwidth is very small. This is not a problem. You can actually have very high coherence time, whereas for light bulb, sunlight, etc., all other routine sources of light that you get, they are actually very incoherent, and they have very small coherence times. All right. And how we deduced it? We deduced it by taking the maximum out of phase frequencies. Okay, when the frequencies becomes completely out of phase. All right. Now the spatial coherence depends on the emitter size and the distance. Remember that we conceived of the idea of a spatial coherence area. So this is given by the Van Sittert-Zernike theorem, which states that the spatial coherence area is given by this particular parameter. Now, if you look at this parameter, d, the small d, is the diameter of the light source, right? And capital D is the distance at which you are monitoring it. And this omega that you see over here is small d square by capital D square. So it's basically the light source divided by the distance at which you are kind of trying to monitor it. So it is basically nothing but the solid angle subtended by the source. It's a solid angle that is subtended by the source. So if you look at AC now, if you look at this, you get lambda square divided by pi into the solid angle. So basically what happens here, if you look at it carefully, the wavefronts smooth out as they propagate away from the source. So that means, what happens that as the solid angle becomes larger and larger, okay, the solid angle, so as the other way around. So you can see that as the distance becomes, as you go on moving the distance, okay, that is that d. So what happens is that this solid angle becomes smaller and smaller, right? As a result of that, okay, this particular coherence, spatial coherence area becomes larger and larger. Okay, it's other way of saying is that the wavefronts actually become very smooth as they propagate away from the source. It is also a function of the wavelength. That means larger the wavelength, okay, more is the spatial coherence area. Okay, another way of telling is that greater is the d, or further away you are r from the light source, greater is the coherence area. This is precisely happens with starlight. They are spatially very coherent because the stars are very, very far away. Okay, very, very far away means this d is very, very large. Okay, very, very large. And this small d is of course like the star, whatever is the dimension of the star, like the light source. So in other words, you don't even have to go to the star. If you are sufficiently further away, your spatial coherence is very high. Okay, and also smaller is the light source. Okay, more is a spatial coherence. So all these things are captured in this particular slide. So two other things, that when you actually have sum of two waves, which we were kind of doing, that is interference, which we talked about earlier. So if we look at this particular part, okay, you will find that if I make it red color, second. So if we look at this, you will see that when you have same polarizations, we already talked about polarizations earlier. This is coherent addition, same colors. So same polarization, same color, you get an addition, and then you actually have the other term, right? It's not just an algebraic sum, but it is also the other terms that comes into the picture. It's when you have different colors, when you have incoherent addition, when you have different colors, it's just the sum. And when you have different polarizations is also the sum. When you actually have different polarization, different colors, you have just a simple sum. So interference occurs only when the waves have the same color and same polarization. This is also to be kept in mind, that when it has got same color and same polarization, then only the interference will occur. Okay. So interference of waves. So most light will have interference for very small optical. So coherence is that most light will have interference for small optical path difference. Few wavelengths. Remember, it's an integral multiple of the wavelength because the phase is not well defined over long distance. Okay, so that is why most light comes in short bursts strung together. So this is, for example, the incoherent light from a light bulb, and you can get this random phase jumps because the phase is not well defined over very long distances. Okay, all right. So this is more on the interference and on the coherence. The laser is of course an exception. It's a coherent light source, so we already know, and this is also going to be very useful when you do the PTPA and the LTV. We look at a little bit about what we call this thin film interference. We have seen the effect of different colored reflection from thin oil films or from soap bubbles. So for example, this is a film. Okay, this is oil on water, for example. So there is water, and then there is oil, and there is light. So part of it gets reflected, part of it gets refracted, then comes out and then gets refracted. Part of it goes refracted, then it undergoes reflection, then again it undergoes refraction and stuff like that. So the rays which are reflected of the lower surface, which is this lower part, travels a longer optical path than the rays which are reflected from the upper surface. Okay, this is known. So if the optical paths differ by multiple of lambda, the reflected waves add, and if the paths cause a phase difference of pi, the reflected waves will cancel out. Okay, so this is the thin film fundamental. So, for example, here ray 1 has a phase difference of pi upon reflection. Ray 2 travels an extra distance, which is 2t, there's 1t and then 2t twice, and normal incidence approximation, and this is 1, and this is, say, for example, oil on water or optical film on glass soap bubble. So the constructive interference happens when rays 1 and 2 are in phase, or in other words, this 2t that it suffers is an integral multiple of the lambda n, okay, plus that's half lambda n, or so lambda n is nothing but lambda by the refractive index. So this 2nt becomes equal to m plus half into lambda. So this is the constructive interference theory. All right. So this is the constructive interference theory. And so as you can see that this undergoes a phase change of pi, and then it has the 2t distance. That's what we are kind of adding over here. Okay? So the destructive interference part will happen when the two rays are pi out of phase. In other words, is 2t is equal to m lambda n, which gives rise to 2nt into m lambda. So this is the thin film interference profile. So when ray 2 is in phase with ray 1, they add up constructively. We see a bright region. The different wavelengths will tend to add constructively at different angles, and we see bands of different colors also. So oil on water, optical film on water, the thin films work with even low coherence light as the path lengths are really short. Okay, when ray 2 is pi out of phase, the rays interfere destructively, and that's how anti-reflection coatings actually work. So this is the anti-reflection coating that is used routinely. So you see that there are optical explanations behind each and every one of them. Okay? And this is very common because when you do thin film interferometry, this is the technique that is used. This is used, for example, when you have droplet impinging on a pool of liquid or droplet impinging on a surface, and we can see very intricate features because these are also dynamic. Here, of course, it's a static example. The film is static, it's not moving. But if the film was also moving, and if you have a high-speed camera to continuously monitor it, or high-speed detectors, you can actually find out the dynamics of this thin film, which may not be possible with your normal camera. Then we talk a little bit about the Michelson interferometer. So it basically uses a beam splitter to create two optical paths. So this is the input beam, for example, okay? And then there are two mirrors. So part of the beam, so this is a partially coated mirror. So part of the beam goes to one mirror, part of it gets transmitted to the second mirror, then they get reflected, recombined, and that is what you see as the output. So this is like a beam splitter. So the output beams are perfectly aligned. They will interfere uniformly, giving either a bright or a dark output, depending on their relative phases. Okay, so these two mirrors are at two different path lengths, essentially. But usually the beams are a little bit misaligned to begin with. So this is input. So this is the output. So interference of misaligned beams, we already know. So these are the beams which lines represent the maxima, and this is the beam for the other beam which leads to the lines with maxima. And as they kind of interfere, what you will have regions of high intensity. Okay, unlike the perfectly aligned situation. Okay, and you get these fringes that you get. So with this, you get the fringes. This is already something that we know. So you can do optical testing with a Michelson interferometer. It uses a beam splitter to create, as we see, the two optical paths. The same can be used for testing optical windows. So you can choose an optical window. If the window distorts the waves, they will show up as interference fringes. So this is a good window. This is a bad window, for example. All right. This is also the Newton's ring that you can see over here. And Newton's rings are also, it's almost like a thin film. So you actually have a curved interface right now. So the get constructive interference when an integral number of half wavelengths occurs between the two surfaces. Okay, so this is basically the back surface reflected beam. This is the front surface reflected beam. This is the incident beam. So you will see color lambda when constructive interference actually happens. And this is what you see. You will see bold colors when m equal to 1. Otherwise, variation with lambda is fast. This effect also causes colors in bubbles and oil films on puddles. So you can see these are real life examples where we can see that why the Newton's ring, I mean, this is called a Newton ring, but it's essentially also a thin film interference, okay, which we already talked about in these previous slides. Okay. In the Michelson interferometer, you can also do one thing. You can jitter the mirror also. That can also give rise to, changes in fringes. You can test windows. You can use this, for detecting very small spaces. And this is routinely, as I said, routinely used for droplet impingement. So we finished the lecture here. This covers a lot on interference and coherence, just to give an idea that what things are. Of course, we have skipped the math as much as possible, but we have given a little bit of an idea of what this is. Okay, so this will be handy when you do PDPA and LDV and any other measurements, as a matter of fact.